To start the discussion, we should begin by understanding what a recurrence relation actually is. Suppose we have a sequence right here. You might say, wow, that's just 2 times the previous number plus 1, right? Of course, but would you really want to write 2 times the previous number plus 1? We could make this simpler by using a recurrence relation, where 1 can be a subscript 0, 3 can be a subscript 1, and so on and so forth, as long as the first term is a non-negative integer, and the rest that follows are larger than or equal to that. Before we get into the maths, let me show a well-known example of a recurrence relation. So other than the well-known Tower of Hanoi, which many of us are familiar with, here's a story I read in a book as a child, which involves the same idea of recurrence relations. To give a bit of a backstory, this is the tale of how a king rewarded a mathematician after being introduced by him to a game of chess.
Wow, this game is nice. What do you want your reward to be?
I want this to continue for the whole chessboard.
Okay, is that enough?
Yes.
More. Stop. Why is there so many rhymes?
My eyelash.
Ow, my sports everywhere.
Mamma mia.
Why must you make me
It
suffer?
has only insert two chess boxes.
I have made a mistake.
The concept of this is simple. What seemed like small numbers of 1, 2, 4, 8, and so on and so forth, of each chess box expanded into numbers beyond our comprehension. But what is the exact number that the king would have to give? As we mentioned earlier, we could first work out a recurrence relation and apply that to devise a formula for this. To find a recurrence relation, let's look at the first few boxes. The sum of all the rise when we total up the boxes and the ones prior is as such. Because we start with 1, we can say that r subscript 1 equals to 1. Now comparing it with the second box, the total number of rise so far is 3. If we look at it from a different perspective, the number of rise currently on the board is twice the number of rise from r subscript 1 plus 1. We put r subscript 2 equals to 3. Comparing it with the third box, a formula to get the value is to just multiply 3 by 2 and add 1. This works the same for r subscript 4 and r subscript 5. Now we are confident with our recurrence relation. The total number of rice when we are at box n is 2 times the total number of rice when we are at box n minus 1 plus 1, or in a recurrence relation, the formula below. A recurrence relation may seem fine, but to manually calculate this 64 times can be cumbersome and prone to error, especially when we're working with such large digits. Thus, we could try solving this iteratively to get an explicit formula to directly get the total that we would want to calculate in an instant. To do that, we could repeatedly express r subscript n in terms of the previous terms of the sequence. We return to our recurrence relation, but let's say we want to calculate up to box n. Thus, we plug in the numbers. And since we know that we could do the same for r subscript n minus 1, why not plug that in as well? We know that this goes on for quite a while, so we could find patterns and use it to our advantage. And we soon come to a formula that repeats itself for every iteration of the formula, calculating it. Conveniently, we know that r subscript 1 is 1, so we get a relationship as such. Now, how do we simplify this? Remember that we have learned this formula in our previous chapters, so for each increasing n, the total will always be 1 less of 2 to the power of n. And there we have it. The final formula for this equation is 2 to the power of n minus 1. N in this case is 64, so we calculate this and I'm not going to read these numbers, it's directly on the screen. Yeah, good luck. To put it into perspective, if the king were to finish filling it up to box 64, the number of rice needed in total is 2,000 times the annual wheat production in 2021. Guess the king should have taken a few maths lessons before agreeing to the deal.